I don't know how that worked, but yeah. So I ended up doing a joint partnership between the University of Strasbourg in France, where I was sent there to really learn the science, and then take that learning to Australia and set up a lab at the University of Wollongong. It's just south of Sydney, in New South Wales. So I was to take my knowledge and sort of bring it to Australia, where all my sites were. So I did some preliminary research in the Himalaya. So while I was waiting for my Australian experience, I had 9 months to sort of get used to the science. So my supervisor gave me some samples from the Himalaya. So that's sort of how I'll start my journey, and then we'll move into Australia. So let's just have a quick look. I'll introduce chemical weathering because that's sort of the basis of the talk. Soil is formed through chemical weathering. So we'll talk just very briefly, I guess, about the background and the significance. And then there's some classical approaches that are typically used to quantify chemical weathering, which is a pretty difficult process. And my proxy was boron isotopes. And I'll explain why I'm using boron and where it comes from. And that's sort of my approach. And then we'll look at the research objectives, and then just briefly talk about the analytical stuff, like how I did it, the machines that I used, and then my sites. So the modern sediments that I'm looking at come from the Gandak River in the Himalaya Mountains, and then the Murrumbidgee River in Southeast Australia. And then the final bit, we'll be looking at Paleo Channel deposits. So a Paleo Channel is just a river that's long past its due. Water no longer flows there, but the river essentially has choked itself out with sediment. So all that remains is sort of like what you see on the right-hand side, or large sediment deposits that hopefully will tell us something about past climate. We can understand how soil was forming in the past, and get some information using boron isotopes. And I hope I've put together a slide as well looking at the applications to Southwest Florida. So I sort of sat the last few days and tried to come up with a few points how this work would relate to us locally here. And that will sort of lead into questions. I'm trying to seek more information, and you folks would probably be good people to chime in on how I could apply this more locally. All right, so let's take just a brief look at chemical weathering. This is just, it's a major process on Earth, right? And essentially this is where Earth's surface becomes uplifted. So you build mountains, then the rainwater dissolves the rocks because it's slightly acidic. And then these rocks disintegrate, and all the ions that were in the minerals get washed away into the rivers, and then eventually into the oceans, where they become part of the shells of animals. And some of it gets buried in the seafloor, and eventually that will become recycled. So that's just sort of how chemical weathering is part of the carbon cycle, and just recycles material on Earth's surface. So why is it important? Most importantly, it provides nutrients for plants and animals by the creation of soil. So that's sort of a big one, especially here. Everything really depends on soil, as you know. So studying chemical weathering and its processes give us information about soil formation. Secondly, it's a key process in recycling elements on Earth's surface. We know that the surface of the Earth is very dynamic, and the landscapes are always changing. And chemical weathering is a very big part, along with erosion and physical weathering, of changing the surface of the Earth. And then ultimately that really does affect the quality of soil and also the health of our water and the amount. And ultimately, what I'm really interested in is this last point here, and that's looking at how chemical weathering has a strong link to climate. Because if you look here at this next diagram, We know that chemical weathering consumes carbon dioxide. So carbon dioxide and water in the atmosphere blend together to make carbonic acid. That's the acid that eats away at the surface of the rocks and ultimately ends up consuming carbon dioxide. So if you draw down carbon dioxide, the temperature of the Earth is going to lower. So as we are putting greenhouse gases into the atmosphere, and as volcanoes release that into the atmosphere, chemical weathering balances out that budget and brings the climate down. So that's the intimate connection between them. But studies have a really difficult time understanding how this really works, like the speed at which it works, which minerals weather faster. So they try to do some lab studies that replicate chemical weathering in the lab. But the difficult part is that when they apply it to field sites, it often fails because chemical weathering responds to temperature, but temperature is really interdependent on other environmental factors. So it's hard to quantify it. So that's a sort of a new branch of science that looks at quantifying chemical weathering to figure out how fast it's happening, and what exactly is the relationship to climate. So some of the basic approaches that have been used, the most common are looking at chemical elements. So major elements and trace elements, whether they're in sediments or they're in soils or even river water, can give you a lot of information about the weathering regime. So how it's weathering. My approach is looking at a non-traditional approach, looking at stable isotopes. So this is a really new branch of science. And sort of there's different materials, like I mentioned, that could do this. So maybe soil profiles locally, the dissolved load of rivers. So those are all the ions that are floating in the water. But I'm going to focus on the sediments themselves. The clays that are in the water form from chemical weathering, the silts, the sands. I'm trying to get information about those guys. And you could do it on a number of scales. So the very minute scale, like in the lab, would be looking at minerals. My boss did it on soil profiles in France, but I'm going to look at the catchment scale. So a whole drainage basin. Studies have even looked at the global scale as well, trying to extract weathering information, studying like very, very big rivers like the Amazon or the Mississippi River, the Ganges River in the Himalayas. These guys transport massive amounts of sediment. So the stuff coming out of those rivers really gives you information about global scale chemical weathering. But I'm going to scale it down and look at a small river. First in the Himalaya, and then down in the Murrumbidgee in Australia. So here's some examples of timescales. You could either study this really on a geologic timescale. So that's what you're seeing on the right there, looking at millions of years. Most people look at this because we know, of course, geology happens over very, very slow periods of time. So the thought is that chemical weathering responds to climate, but over a really long time scale. The newer studies that have come out have actually contradicted this and said that you could quantify chemical weathering on 100,000-year time scale. So this is a glacial to interglacial time scale. And that's what my work is going to look at, to see if the landscape actually responds, or chemical weathering actually responds to much shorter time scales. So that's what I'm going to do. So looking at a 100,000-year record could give you that information. So why boron isotopes, right? Boron is the fifth element. Boron comes mostly in minerals. So you'll find it in all sorts of earth minerals, in soil and in sediments. There's a lot of boron. And boron can be used as a proxy for chemical weathering because it has a large isotope fractionation during water rock interactions. So what does that mean? There's two isotopes of boron. So there's 10 and there's 11. And when water sits in contact with soil or with sediment for a long time, there's preferential isotope fractionation by 10 boron. So in nature, there's a very large range of about 70 per mil in nature. So for instance, in soil profiles, on the bottom left, you could see here, if you were to study the sediments in there, you would typically see a composition of about -10 per mil in sands, while the clays have a much more negative signature, about -25 per mil. So that means that when these clays are formed, they're absorbing more of the 10, and more of the 11 preferentially goes to the solution that it's in contact with, like the rainwater. So it gives you a really good proxy to study chemical weathering just due to that large isotope fractionation. And then also during vegetation, so like that tree, for instance, all the soil that's underneath there, boron is being cycled through that tree. So if soil is forming underneath that tree, it preferentially gets enriched in the other isotope, in 11. So it gives it a very positive signature, for instance, like +35 per mil, which is really different than, for instance, -25 in soil profiles. So it's this large isotope fractionation that makes it a really interesting element, because it has a lot of capability to give you information about what's going on. So I'm going to use that symbol up in the top right, that delta 11B, with that little symbol that looks like a percentage. And we're going to use that throughout the presentation. So it's delta 11B. Okay, so what my research tried to do was look at three topics here. I wanted to gain information about the parameters that control isotope fractionation in modern sediments, and I wanted to understand how these sediments record that weathering regime. Secondly, I wanted to understand how that signal carried by the sediment is carried by the river sediments. How's it transported from where it's formed in the soil to where it's deposited? And then finally, I wanted to see if we could use boron isotopes as a proxy to reconstruct paleo weathering and paleo environmental conditions. So I want to see if this is a good proxy to understand or to reconstruct the past weathering regime, the past environments. So this is what we did. We took river sample sediments on the banks of the sediments. I'm sorry, on the banks of the rivers, like on the left. So there's us collecting some sand and some river deposits. We also took water samples, like in the middle. And then finally, there's the Paleo Channel samples. So we drove these large core pipes into these sediment deposits down profile. And we wanted to see if these different sediments could give us any information about past climate. So this is the analytical technique. We took this dirt, or this clay. Usually we extracted the clay out of it. We baked it in the oven. Then I did some ionic exchange chromatography, just trying to isolate boron from all the other elements. And then I ran it on this ICP-MS. So this is a big mass spectrometer machine that ionizes the sample. You put it in, like where you could see there on the counter, you run it through a really hot plasma, and then it uses electricity and magnets to separate 10 boron from 11 boron, and it collects it in the little cups. On top, you can see our little, our mascot was a wombat. It's a little Australian creature that looks sort of like a pig almost. And if he's in the lab, that usually means you're going to have good results. So there's our mascot wombat, Jeff. So here's our first sample. Our first site was from the Gandak River, high up in the Himalayas. So it spans Nepal and India and Bangladesh. And there's some, I didn't get to go there, like I said, these samples were already in France when I arrived. It would have been a super cool trip, but they sent me down under instead. So this is what our field site looked like. And these red dots are where I took my samples, or where they took their samples. Some bank sediments and a few suspended load samples from the headwaters high up in the mountains, all the way out to the Ganga Plain. And then this river eventually meets up with the Ganges River and dumps into the Bay of Bengal. So this is the one of the main tributaries of the Ganges River. So here's what my isotopes look like on the left-hand side. So again, we have that delta 11B, and we normalize the clay fraction to the sand fraction, because the sand fraction never really changes, but the clay fraction does, because it takes on a different signature based on how much it's been weathered. So this is positioned downstream on the X and a boron isotope composition on the Y. And what we see in the headwaters, we have a very light signature, and then it sort of evolves down plane, but then it plateaus. So what does this mean? This could potentially indicate that these clays in the river might be a mixture of clays that have a different weathering regime. Means that they're integrated from all over. Like imagine this river is taking sediment from this huge, huge mountain catchment and dumping it all, and then it's working its way downstream. But along the way, some of this sediment might be reworked. So it might be, manipulated on the plane, or there might be actually chemical weathering happening during transport. And both of these processes would be bad, because that means that it's not really recording the conditions in the sediment, in the soil profile. It's changing along the way. And ultimately, we want to use these sediments to record past environmental conditions. But if they're reworked, or if there's weathering during transport, you can't do that. The signature is being rewritten during transport. So we also looked at major and trace elements. Nothing really major that we found, but our results looked similar to a study that you see here in the middle. So you just put boron over aluminum. This is a chemical ratio that indicates weathering, and aluminum over silica on the x-axis looks at grain size. So a higher alumina over silica ratio means your sediment is finer, like your clays, and a lower one means that it's more coarse, like your sand. So ours look very close to what we saw. Means that as you go from the coarse end member to the fine end member, so from your sands to your clays, that diagonal sort of mixing sorting line is what we see in our data as well. So it looks like it's being mixed or sorted along the way. So we're getting some information on the weathering regime from the Himalaya. So then I took that to Australia, right? How could you take this knowledge and apply it to the Murrumbidgee River in Australia? So first off, why Australia? What's so important about this river? It's a small little river, part of the Murray-Darling Basin, and it's part of one of the major drainage basins in Australia, which that doesn't say much, because there's really no large rivers in Australia. Everything is really dry. So we took some modern samples of this river, but more importantly is downriver, we have those Paleo Channels that I was talking about. These really ancient sediments that were there, that were deposited over the last 100,000 years. So we'll look at the modern river, and then we'll see if we could get any information about those Paleo Channels. So this is sort of what the river looked like. The pictures on the left are the headwaters high up, well, relatively high up compared to the Himalaya. It's not very high. But these mountains actually do have a ski slope on them. So Australia is pretty temperate, but in the winter they do artificially make snow high up. And then on the right-hand side is what it looks like on the plain. It's wider and it's quite lazy. Here's me really excited getting samples on the bottom right. And then in the middle, you have some roos, and those roos are does, and they're sleeping kangaroos up high up in the mountain. It was kind of cool to see them. So here's where we took our samples. Those red dots are the main river and also in the tributaries. And we're trying to understand how the signal changes from the soil profile to where they're being deposited way downstream. We separated them. We separated the clay from the sand, just like we did in the Himalaya. And we found that the sand doesn't really tell you too much. It looks like the bedrock. But the interesting part is the clay. The clay is produced by chemical weathering, so that records any sort of signal, any sort of chemical weathering signal. We also took bedrock samples and a few water samples. We also looked at what are called monolithological catchments. That's just a big fancy word for little catchments that contain one type of rock. So you're looking at a map of the headwaters of the river. The colors behind there are different lithologies. So some of it is sedimentary rocks, and some of it is granite, some of it is volcanic. And the little hashed areas are the areas where we sampled. We want to get a representation of what just this pure rock looks like before we can make some estimations of what's going on in the river. So we looked at lithology, and we also looked at elevation. So there's a dotted line there on the map that says less than 100 meters of elevation, so that's pretty flat. Not compared to Florida, but it's pretty flat. And then the right-hand side of the map are higher elevations. So from 600 to over 2,000 meters of elevation. So what we found is there's two graphs here. The one on the left is a graph that looks at the delta 11B of clays on the y-axis, and the bedrock. We normalize it to the bedrock. And what we found is that HEC means higher elevation catchment, and LEC means lower elevation catchment. And then those different symbols are representative of different types of rock. So what we found is that the higher catchment actually looks quite different than the lower catchment. So right away, we see that there's a difference between if you're formed high up in the mountain or lower on the plain. And then we also see, if you look on the graph on the left, you also see that the HEC, those blue triangles, are granite. And that's showing that even though if you're granite, you still have a different signature, regardless if you're in the high elevation or you're in the low elevation. So that's maybe indicating that there's also some differences with lithology. So we see that there's, like I said, a lithological dependence on the weathering regime or control, and also topographic. So elevation, high or low. I'm going to superimpose a graph onto the graph in the middle here. So we see the same thing in the middle, but when I press the button, I'm overlaying Gandak data. So this is data from the Himalaya, and it shows the same pattern as we see in the Murrumbidgee. We're seeing that the boron isotope behavior is same in both rivers. So kind of cool. So I published a paper on this, mostly stating that the high elevation looks different than the lower elevation, and that depending on what type of rock you are, your boron isotope signature is going to be different. This is what my isotope data looks like in the middle. So here's the clay fractions from 0 to 700 kilometers downstream. And on the left are our waters. And the first thing that we notice is our waters look really different than our sediments. Typically, there's about a 30 per mil difference between clays and water, but we found a lot more. Like our water are those black dots on the left. They're at about 30 per mil, where our clays are much lower. They're minus 18, maybe minus 12. So there's much more than a 30% difference between the two. This gives us indication that the clays didn't precipitate from that surface water. There's some sort of disconnect between the water and the clays that form them. That's a first big finding. I created this sort of mixing model, and I tried to understand, or try to see if we could explain the data that we found. So the x-axis is our measured data, and on the left is our calculated data. So I took all information from the catchment, and I see if I could explain what happened. And I was able to. Whether I looked at my clays on the top left, I also did the same thing with major and trace elements. And on the bottom right is even my sand. And what I found is that everything can be explained as a mixture from different parts of the catchment. So all the clays that were in that main river came from different parts of the catchment, and the signal that we saw was just a mixture of them. So that's pretty cool. It was really good. It shows that we could probably use this proxy to look at past climate, which brings us to the last part of the talk, is our paleo channels. And that's what we have here. So these are different paleo channel systems. Again, they vary between modern systems, and they go back. So the one on the bottom is our oldest. This is about 100,000 years ago. This was deposited. So a climate that looks similar to ours, but not quite the same. And here's some more paleo channel deposits. It was a really great experience. We spent I went out there twice, about 5 days each. So the field campaigns were a lot of fun. So we saw a lot of sheep. We did a little bit of drinking in the bar. We met some locals. We got stuck in the mud. I had a really good experience with a good mate of mine. So when we were out there, here's our site map. So these are the paleo channel systems, and I color coded them. So the one on the top in yellow, we sampled them throughout the course of their stream. So that's the Gum Creek. The red stars are our Coleambally, so they're 35 to 55,000 years ago. The green are our Coleambally, and then our blue is our Yanko system. So these span a whole glacial system. So we wanted to see if the sediments are the same throughout the course of the paleo channel, and can we detect changes between them? And if we're able to detect changes between them, could we relate that to past climatic conditions? So here's what we found. On the X is our delta 11B of our clay again. This is our proxy that we're using. And then on the Y is depth. So the top is our surface, and it goes down about 7 meters of our systems. And here's all the different sites that we did. And again, they're color coded. The blues are the same system, the pinks are the same, oranges, blacks, and then I even took a couple of samples from our modern river. And here's our isotope composition. So that's what our modern system looks like. You're at about -10 per mil. It looks just like a modern river, really no surprises. Here's our first paleo channel system. So this is the Yanko between 13 and 23,000 years ago. This is our last glacial maximum. It was extremely cold during this time. And you have a very narrow band. So maybe -12 to -9. And with our proxy, that doesn't really mean much. So we got a really good representation throughout our soil profile. So it looks like things aren't changing, except for that site that you see on the right. This is a site that's quite shallow, and it looks like it might have been altered after the sediments were deposited. That's our first system. Here's our second system, the Gum Creek. Again, most of our sites look just like the previous site did. There's not too much variation between sites, except for the one site that's circled up there. And again, we think that something was going on at that site. It was probably altered after it was deposited. Our third site is our corroboree, and we had two. So we had the corroboree pit. That's what you see in the middle there. And then this headless horseman site that again looks to be a bit altered. Our last site is our Coleambally. This is our oldest site. So there was 3 different sites here. It's our oldest system, and everything looks to be quite similar in that one as well. So let's take this graph away. That's all of our total data. And what you really see is that each system has more or less their own signature, except so the modern Murrumbidgee, the Yanko, and the Gum Creek look at about -10. That looks very similar. The corroboree looks a bit unique. And then the Coleambally looks a bit as well, as it becomes isotopically heavier as it got older. So that's good news. What does this mean in terms of climate? This is a few last slides, and then we'll get to how can we apply this to Southwest Florida. So you're looking at here on the bottom is our ages. So from 0 to 120,000 years ago. So this is an entire glacial system. And then on the Y is our boron. So it's delta 11B from the clay. And again, we just normalize it to our sand. And it's the difference between the sand and the clay that we're interested in, because that shows chemical weathering. And if you look on the left-hand side, so as you go more negative, that means there's more of an influence of water-rock interactions. And as you get higher up or more positive values, you have more of an interaction of vegetation. So I took our data and I superimposed it on a vegetation record from South Australia. So this was a sea core, this is a sediment core taken in the Southern Ocean. And we're looking at pollen. So this is a percentage of trees to shrubs. So when the line is higher, it means there was more trees. Trees means that the climate was warmer, more moist, more humid. And as you get lower, as you get closer towards the bottom, that's more shrubs. Means that you're looking at a drier environment. You're looking at only shrubs are only existing when it's very cold, typically. So our data really matches quite well with this vegetation record. So this is good indication that boron could be used as a proxy, because we see a covariation between this vegetation record and the weathering signal that these clays are giving us. So this first evidence looks like there is a strong influence of vegetation on our soil. So times when there's a lot of heat and a lot of water, this vegetation is really impacting the amount of soil that's formed, and it leaves a strong imprint. But if you look at our colder system at about 20 to about 40,000 years ago, this is a time when the Earth was extremely cold. And what we only see are those really low boron values. Means that the clays are only recording that water-rock interaction. It shows that there wasn't much vegetation on the landscape, and the clays aren't recording it. But during warmer times, so at about 50,000 years ago and at 100,000 years ago, the climate was more similar than today. Means that our vegetation today looked more or less alike, but 20,000 years ago it didn't. So we're on the right track. We might be able to reconstruct vegetation on the landscape by using boron isotopes. And then I finally compared it to sea surface temperature. So this is, again, from the Southern Ocean, and this is a funnel-based record. So they used what are called forams. And they're just little microscopic organisms that make a shell. And these shells, depending on what species is formed, gives you information that could be, that it could indicate sea surface temperature. So again, when we overlay our data on the sea surface temperature record, we see that there's, again, a really strong covariation between what we see in our boron isotopes and sea surface temperature. So what does this mean? Well, I'll go back. It means that it looks like as time goes on, these boron isotopes are able to record climate. There's some sort of some sort of correlation between the climatic conditions and what our boron isotopes are telling us. So we think this is only the second study that did this. There was one previously done in China that had similar results. So we think that we could look at past sediment or past soil, and that could give us information that we could use to reconstruct environmental conditions, because it matches the vegetation record, and it matches pretty closely with the temperature record. So during times, again, when it's warmer and wetter, we see that in our soil, we see that in our clays. And times when it's cooler, we don't see that. So in our black system and in our orange system, that's the Yanko and the Gum Creek system, we only really see the influence of the water and the rock, so water-rock interactions. But it becomes much more interesting as we get warmer, because we could see the difference that the vegetation is imprinting on our soils. All right, so what do we take away from all of this? In our modern systems, again, the paper that I published really emphasized that depending on what types of rocks you have and where they're located, that plays a really big, that impacts quite a lot the weathering regime of these clays. Finally, we know that the boron isotopes in the river sediment don't evolve over time. I didn't go into too much detail into that mixing model that I used, but I said that I was able to explain all the data that I had just using other measurements in our drainage basin. So it means that when the sediment from the modern river gets deposited, it doesn't change over time, which is really good news. It records the conditions of formation. The sand really only represents what the bedrock looked like, but the clays record what was going on at the time of formation. So really cool. And then our Paleo Channel sediment study, this is work that I'm still trying to publish. So it's the second major chapter of my doctoral thesis. And the results are good. They indicate that the boron isotopes in these clays may be a potential proxy that you could use to reconstruct the past. You could reconstruct what the vegetation was like, and you could reconstruct how intense the weathering regime was. So that can give us information about what the landscape looked like or how the landscape changed over time. And then finally, we saw that there was covariation with both climate, so that's sea surface temperature and vegetation. And it indicates that the weathering regime actually is responding to climatic variability. So it responds during cold times, and it responds via vegetation during really warm and moist times. So we think at the moment, I'm trying to get this work published, that this is a good proxy to reconstruct the past. And finally, I haven't put too much into this, but I was maybe, I guess, trying to seek your input on how we could apply this to Southwest Florida. So I'm an instructor at FGCU, meaning that I only teach. But my passion is really research. I want to get back into research. I have a PhD, and I'm looking to use, obviously, this 4 years of really intense training and apply it locally to soils here in the area. So here's the final slide, and it's just some things I was thinking about. So I thought maybe just getting a general knowledge of soil compositions here in Florida, we could put that to multiple uses. Maybe looking at differences in landscaping, maybe the agricultural community could use it. For instance, like the citrus growing folks, like I have the soil core here on the right, and I thought if we know more about the soil composition, I might be able to help, maybe, I don't know, maybe grow better citrus or help with sort of the economic impacts. That's sort of how you could justify your work, right? If you could relate it to the economy in any way, people will fund you. If you don't, you're sort of pushed off oftentimes. That's sort of a good in. We have a really big agricultural industry. Also, I think maybe just getting a better understanding of local soil formation processes and conditions could help. And if you apply uranium isotopes to these types of studies, you can get the rate, you can get a time series. So that can give you an information at how fast things are evolving over time. And that's what my supervisor in Australia did. He used uranium isotopes to put a time frame to these soil formation processes. Boron isotopes can't do that. You need to couple them with lithium isotopes or with uranium isotopes to get a more robust feel of what's going on. We could also investigate the weathering regime. We could investigate erosion, sediment transport throughout our landscape. So if we were to study like local rivers, we would have a better understanding of how sediment is being transported across our drainage basin. And that can give us more information on how the landscape is changing. And finally, I would love to do some reconstruction of paleo environmental conditions here in Southwest Florida. So we have a pretty robust history going, as far back as the Calusa Indians, for instance, and knowing on how the environment changed and how the environment looked like going back thousands of years could provide a lot of, scientific information, but also historical information about how our landscape changed over time. So I think that this might be a good proxy to use to create some paleo environmental conditions in our past. So I also leave it open. Maybe questions could focus on how we could use this information to do other things. So I'm gonna, if you want to, maybe I could turn this back to the host, or we could all turn on our microphones and talk about any of this work. So let me do that. Let me go back to my web browser. Back to Zoom here. And maybe if you want to unmute yourselves, I think you could do that. Let me see. I go to new share. Can't, I want to stop sharing. Share screen. So I gave multiple people the chance to share their screen. Maybe when we want to unmute yourselves, could we do that? I don't think we could.
I think Marlene to give us our.
Could we start talking?
Yeah, we can. We can talk. I just don't think we can videos yet.
What's that?
I think that we can ourselves, but I don't think we.
Okay. So Sheen Square. I don't.
We have can you hear me? This is Richard Malsbury.
I can hear you.
I was wondering if your boron isotope process could be used to look at the different features of Florida limestone, which is basically the stone that is in Florida, which is fossilized sea. And if that could give you information on the ages of the stone, and I don't know if it could do nutrient quality as it breaks down, which would be important for vegetation concerns.
Yeah, I think they could. Yeah, so limestone is a type of carbonate, and you could record both a vegetation and a chemical weathering record in carbonates. Yeah, definitely. And I think that could give you information about how that limestone has been changing over time. Was that your question?
Yeah, and as it breaks down, if there are different nutrient levels during the dissolving process, that would be beneficial to look at in terms of the types of vegetation that it would support.
Yeah, I think that I do think that this proxy could do that. Yes.
Okay.
Yeah. I haven't done it, but most of my work was on silicates, so on clay minerals and stuff. But yeah, other people have done it, and I think that you can get sort of an idea, like you said, of how those nutrients break down. And I don't know, I'm not a plant expert or a botanist. I think maybe giving my record to somebody who can interpret it better in terms of what vegetation it could support, like partnering maybe with the University of Florida or with people who really know what plants need what nutrients. But this could sort of give them the information that they may need. And also, not only boron, but you could do other major and trace elements like phosphorus, like nitrogen, like calcium, all the magnesium, manganese, everything that the plants need could also be investigated, just looking at major and trace elements.
Good. Mm-hmm. Also, I understand that most of the sand on the Florida beaches is basically from the Appalachian Mountains and transported as it's broken down. Exactly. You know if that's true?
That is true. Yeah. Yeah. So we're in Florida. Our sediment really comes from broken down granites from the Appalachian Mountains, and then you have the biological sediment, the biological silica that comes from the Caribbean. So broken down seashells and coral reef. It's about half and half, and it's very acidic, and it's all limestone based, most of it, and then the other half is granitic based, like the beach sand.
And in terms of transportation of the materials, you were talking about clay and sand. Which is heavier? Is the clay heavier and tends to settle out faster than the sand? So the sand would transport faster and longer?
No, opposite actually. The clay is very light, and mostly it floats in the water. It floats in the river, usually on the surface. You could actually get a net and like take samples. They call it like suspended load samples. The sand is really heavy, it's coarse, and it settles to the bottom. But what I did was filter the clay out. So I was taking like riverbank samples and then doing sieving and then doing centrifuging to get only the really light clays. But you have to sieve a lot of sediment to get enough for one boron analysis. Quite a lot.
Thank you.
Mm-hmm. What else?
Any other questions?
Anything else? I know it was a lot to to take in.
I think he has a question. Chat.
Yeah.
Do you ever study farming cocoa boards as how they can lock up carbon dioxide in the atmosphere and calcium carbonate?
I haven't. No, I did. So my undergraduate degree, my bachelor's degree, is in marine science, and then geology sort of took over my interests from that. No, I haven't. But what my boss did in Australia, he was studying organisms like that could sequester carbon dioxide and produce oxygen. So these are the original organisms that gave the atmosphere all of their original oxygen composition. I haven't done it personally, though, no. But I think it's very interesting because yeah, these really do, just like chemical weathering, monitor the amount, the ratio of oxygen to carbon dioxide. It's definitely, you could be using that for paleoclimate studies. Yeah.
Thank you.
Mm-hmm. That was stromatolites. The word was slipping me. He was studying the stromatolites in Western Australia in the Indian Ocean.
In terms of citrus farming, I remember reading at the university I was doing. There was a kind of chemical that have citrus green. Are you familiar?
I'm sorry, Cassie. I couldn't hear you very well. You're kind of going in and out for me. Could you say that again?
I'm gonna do it.
We had good sound for a while. What happened to it?
I have no idea what's going on.
So University of Florida is doing research on citrus greening and the benefits of oaks. So I responded to you there. I just simply asked if you think that my research might be able to assist them. I don't know anything about it.
I Not
Not
familiar,
familiar,
Cassie.
Cassie.
What
So
is
Cassie,
what is citrus greening? I'm sorry.
citrus
Citrus
greening is
screening is
an issue with the citrus trees, but Cassie, maybe you can explain. Unfortunately, our sound is very weird.
Yeah, I don't know what happened.
Everybody's muted, so I don't understand.
Yeah, we're all on mute. Some of your work published.
So I don't know how well this is going to come through, but citrus greening, Cassie says, why all oak trees may hold an extract that citrus growers can use to protect their fruit trees from the deadliest citrus crop disease the world has known. The plant disease is called long bean or HLB, also known by its English name, citrus greening. It's also spread by an insect called the Asian psyllid. The psyllid feeds stems and leaves of trees, infected the trees with bacteria that cause citrus greening. Greening impairs the tree's ability to take nourishment, ultimately resulting fewer and smaller over time. Once a tree is infected, there is no cure. For those who don't know, it's basically
Just got better, Marlene.
It is better. It basically is one of the pathogens that's causing the decline of the citrus industry in Florida. Cassie, did you talk about it?
Yeah, I put the article in the chat. There's some extract that's found in oaks that can help prevent the citrus greening. But he had just mentioned obviously the economic impacts of citrus on our state's economy, so it might be something worth looking into.
Yeah, look, anytime you could talk about money, anytime that you can show that science could help people's pockets, their wallets, the economy, you get a lot more attention, right? You'll get the head turning of citrus growing people, of University of Florida. People want to hear, when it directly affects their money. If you can't really show that, oftentimes you're pushed aside a bit. So in our state, it's a really big issue, right? So yeah, any sort of information that could help that industry is a massive benefit, obviously. So that's the kind of work that will get funded and that UF will partner likely with you on.
Does anybody else have any questions for Christian?
Hey, that was great. Thanks so much, Christian, for being with us tonight.
You're welcome. It was great to meet everybody. I hope the talk didn't put you to sleep. I know it was a little different than things you've probably thought about recently, but yeah, it's a new and growing world out there. So yeah, awesome. Well, thank you for having me.
Thank you very much.
You're welcome. Take care.
Thanks, Kristen.
You're welcome.
Take care.
Thank you.
Thank you.
See ya.
Thank you.
So just to remind everybody, next month we have Jenny Evans from the Sanibel Captiva Conservation Foundation, the native nursery out on Sanibel. And Jenny has been a longtime member, and we're really happy to have her talk about, will the real native plant please stand up? So that is going to be talking about native plants and their look-alike, not so native plants. So with that, if we don't have any more questions, any questions, any comments?
I just wanted to say this is my first meeting and I enjoyed it, and it's nice to meet all of you. I also really appreciated, I'm not sure, was it Christopher who made the comment when we all heard echoing and it was so hard to hear for so long, that if the speaker mutes himself while a participant is talking, that gets rid of the echo. You know, this technology, every time I do a Zoom meeting, I'm learning something.
Well, isn't that the truth? And it never seems like we have the same mistake twice, right? So I think, you know, at the beginning of the meeting, we did turn off all the videos and mute everybody. And I think that did help, but I'm not sure what exactly happened. But hopefully we'll get all the kinks worked out next month. And want to thank everybody for joining us. And we'll see you next month. If you are not on the newsletter mailing list, please drop us a note and let us know. You can do that through the contact us on the newsletter. And of course, we have the Cutting Horse facility that's open on Tuesdays and Saturdays from 10 to 2. And we're always looking forward to seeing you there. Anybody else?
Thank you as always, Marlene.
Hey, thanks, Paula. Always good to see ya.
I don't see anybody, but hi.
Yeah, I don't either. I'm not sure what exactly happened there, but yeah. Yeah, I'm not sure what happened, but anyway, thanks everybody, and I'll see you next month. Take care.
Okay, thanks. Bye.
Bye-bye.